Welcome everyone to the Applied Topology Online seminar. So the talk today will be by Žiga Virk, and he will tell us about geometric interpretations of persistence.
Okay, so welcome everyone. Thanks for joining in. As I mentioned in the abstract, I will be talking about geometric interpretations of persistence, meaning that we'll go through this paradigm that in order to compute persistent homology, one typically constructs Rips or check filtration, and then persistent, this kind of complexes should reconstruct our spaces at small scales, but as we are increasing the scales, we are kind of expecting to detect sizes of holes. So we'll actually go through a number of results going along these lines, and just I won't have many formal proofs. I'll just try to give you geometric intuition about how things work out. So here's our plan for today. We'll start with filtrations. Mostly we'll be talking about Rips complexes here. Then we'll go to small scale reconstruction. We'll see a couple of new tricks about how to reconstruct spaces. And these numbers 3, 4, 5 are actually about interpreting sizes of holes and other things that happen. Okay, so let's just start with our setting. We'll start with a metric space, potentially with a subset in there. We'll have a scalar, and we'll construct check complex and Rips complex. These are actually standard constructions, so maybe I won't spend too much time on them. And then we will define a filtration, meaning that as we're increasing the scale size, we get this natural system of inclusions. And these two filtrations, of course, they're different. The check filtration is always different than, well, almost always different than the Rips filtration. These kind of provide the snapshots of, well, kind of a, what's the right expression? Scale-free representation of our space. All right, so the first thing we want to do today is to talk about this relationship between check and Rips complexes. So the check complexes have a nice property, namely they're defined as nerves of covers, which makes the application of the nerve lemma quite easy. On the other hand, the Rips complexes are not really nerves, but their definition makes them really easy to use in, let's say, coding or something like that. So our first goal will be to try to treat Rips complexes as nerves of cover, which will enable the use of the nerve lemma. So essentially, we'll construct a cover whose nerve is homotopy equivalent to a Rips complex. Maybe just a word of warning, sometimes I get this question. Our complexes here will be generally built on the whole space, and our spaces will be, let's say, manifolds or something like that. So we will have infinitely many vertices. Now, how that relates to, let's say, practical setting where we usually have finitely many vertices? Well, of course, as one is increasing the density, using the stability result, the limiting persistence should approach this persistence we are describing here. So in general, we have, infinitely many vertices. Don't be scared by that. Okay, so as we said, first we want to describe Rips complexes as covers. So let's try a uniform approach. This is pure topology school. Let's start with a cover of a space. It's called U. And given this cover, we can naturally introduce two simplicial complexes. One is the nerve of the cover, which we all know very well. So vertices are elements of the cover, and non-empty intersections give us simplices. And the other one is Vietoris complex. So the vertices of this complex are actually just vertices of our space, and simplices are those finite subsets that are contained in some element of a cover. So this thing is very natural, and an old result by Dowker states that these two complexes are actually homotopy equivalent. And I found this result really fascinating, besides the point that it's very old. An interesting thing here is that the covers don't have to be open or anything or constructible. These are just any covers.
Žiga, can I ask a history question?
Sure.
So I know maybe Vietoris or Hausmann use these Vietoris complexes, to do cohomology.
Yes.
Does Dowker call them Vietoris complexes, or?
I think he called them the way I stated them here. I'm quite sure. I'm not 100% positive, but I think this is the old notation that I just stated here.
Okay, cool.
Yes. Yeah, so in some cases, Rips complexes are called Vietoris-Rips complexes. And in this talk, I'll be differentiating between Vietoris complex and the Rips complex. So the Vietoris complex, which is older, actually arises from a cover, while the Rips complex actually just comes from a scale parameter.
Thanks.
But yeah, the funny thing is that they're connected. Okay, just another thing I wanted to mention about the Dowker theorem. The proof in his original paper is kind of longish, but if you use the nerve lemma and use the cover on Vietoris complexes induced by maximal simplices, the proof can be done in a couple of lines. So if you want a proof of this, don't go through the original proof. Just use the nerve lemma and you can pull it off shortly. Okay, so this is a relationship between Vietoris complexes and nerve complexes. And so what we would like to do now is, well, if we have a Rips complex, we'd like to construct a cover whose Vietoris complex is the Rips complex. This thing below is one option. So if you have a cover consisting of all maximal subsets of diameter less than r, or let's say all open subsets of diameter r, depending on some technicalities, then the Vietoris complex of this cover is actually the Rips complex. And if you want a connection to the nerve, well, it's homotopy equivalent to the nerve of this same cover just by the Dowker theorem. So maybe what is missing here is that Rips complex of x at scale r coincides with the Vietoris complex of this cover, and that is homotopy equivalent of the nerve. So this is our connection between Rips complexes and nerves. So an insight, if you make a statement that you want to remember, check complexes actually arise from covers of prescribed radius, and Rips complexes arise from covers of prescribed diameter. So in a way, both complexes are very natural. The only difference is that Rips complexes are usually defined in terms that make them easier to define, just with those flag conditions. All right. Let's have an example. So suppose we have this space. The diameter of this circle is 10. The diameter here is 2, and the gap here is 1. And suppose we're using the Euclidean metric, and we want to check for at least a couple of scales whether Rips complex of x at scale r is homotopy equivalent for x. So for small scale r, for something that's smaller than 1, if you start constructing sets of fixed diameter less than 1, you'll be getting this kind of arcs or intervals in the middle, or this kind of triads here. We'll be getting arcs here and a triad here as well. But the point is that this cover is a good cover. So, and its Vietoris complex is actually the Rips complex. So, since we have a good cover, for these scales, the Rips complex actually reconstructs your space up to homotopy. And then as you're increasing scales, once you go slightly above this gap, constructing covers with sets of prescribed diameter will force you to choose this kind of sets. Now, these are not contractible anymore, So the cover is not a good cover anymore, and especially in this case, it's easy to see that you will actually generate a one-dimensional persistence class. So in this case, you will not reconstruct your space up to homotopy anymore. All right. However, as you move on, if your scale goes past 2, you can construct a good cover again, because the sets of prescribed diameter, well, before some of them had a gap here, but now they're big enough to connect on the other side. So these are actually the types of sets you're getting, and altogether you get a good cover again. So for some intermediate scales, you can reconstruct your space again.
And you're using only maximal sets of prescribed diameter?
Yes, only maximal sets. So if you go through the definition of the Vietoris complex, you can see that you can construct all sorts of covers. You can take maximal sets of this diameter. You can take all finite subsets of maximal sets of this diameter. But if sets are finite, you're not going to get a good cover. You can get all sorts of things, especially in the plane. You can take sets of prescribed diameter. You can just get convex hulls of finitely many sets. I mean, I could probably talk about it for like half an hour. There are many options. But yeah, the easiest one to use is just to use the maximal sets of prescribed diameter, because that seems to have the best chance of inducing a good cover. All right. So that's it. And then when the scale becomes almost 10, sets of prescribed diameter become like this. So these are not 3 different sets. These are one single set. So these are the kind of things we'll see later when we'll be talking about Rips complex of a circle. Again, the set is not connected, which means you're not getting a good cover, and it can actually be proved that, again, we do not reconstruct the space up to homotopy. All right, any questions so far? None. All right, so much about filtrations. Oh yeah, maybe just one slide. Maybe you shouldn't read all of that, but the point of the slide is that we're talking about the nerve complex, and we're talking about the Dowker complex, and in some cases, especially since we have filtrations, one would think about whether these things are functorial, and the easiest way to describe this thing is in such a diagram. So if one has a function between 2 spaces, and the covers on both spaces, so that this inclusion, it's the most natural condition holds, then one gets this commutative diagram, I mean the diagram that commutes up to homotopy. So let's just see what this diagram does. On the right-hand side, we actually have Dowker duality. This is always a homotopy equivalence, and this thing says that this homotopy equivalence is functorial. On the left-hand side, we have this classical map into the nerve. It's induced by partitions of unity. It's a fairly old thing. And if our cover is good, then the nerve theorem actually gives us this, implies that this map is a homotopy equivalence. So in the case of a good cover, we actually get that, good covers are functorial and everything commutes as much as we want. Again, maybe I don't want to go too much into details of this thing. I'll just show you some applications of this thing. But to me personally, this is like the shortest description of the Dowker theorem and of nerve lemma and of its functoriality. All right, so now that we can express Rips complexes as nerves, we would want to use this thing to reconstruct spaces. So the first example we will mention is that of a compact Romanian manifold. So of course, if one is using Czech complex, you can just use the nerve lemma and see that for small r's, we can actually reconstruct the homotopy type of the manifold. For Rips complexes, the same result was proved by Hausmann in 1995. And again, the proof is kind of interesting, but yeah, could be done shorter.
It's impossible to read for me, I would say.
Okay, that's
like it's really hard.
I was trying not to discourage people, but yeah, I mean, here's my proof. I mean, using the previous results. So using the interpretation of the Rips complex and stating that it's homotopy equivalent to the nerve of a cover of using sets of prescribed diameter, we can just take a small r. Actually, the r will be as small as Hausmann's r, and see that these sets, they're like, geodesically convex sets, and they form a good cover, just because things are locally geodesic and everything works out. So you can take, for that cover, generating Rips complexes, you can just take convex hull of finitely many points of prescribed diameter. They form a good cover, and this homotopy equivalence actually follows directly. The fact that this inclusion is homotopy equivalence, on the other hand, follows from the previous diagram, which said that these homotopy equivalences are functorial in a sense. So I get much more essentially for free for using a very small result. And then, okay, yeah, I mean, there is the only thing we're really using here and not proving is the nerve lemma. Everything else actually follows from the slides if you want to prove this result. Okay, so this is the first reconstruction result. The second one I want to mention is the one for metric graphs.
And Žiga, maybe another comment on your last slide.
Sure.
Hausmann's result is really only for the less than convention, whereas yours is both the less than and less than or equals to.
Yes. In the paper, I actually have both conventions, and the proof is almost the same. You just have to be careful about those technicalities.
But from Hausmann's proof, it's not clear at all how to edit it to get the less than or equal to case. I mean, I think his proof sort of can't be edited.
Yeah.
Thanks.
Yeah, thanks for the comment. Yeah, so that's a nice promotion of this proof. It's definitely easier than Hausmann's. All right, so this is the first reconstruction result. The second one I want to mention is for metric graphs. In this case, you can actually completely classify the scales for which you can reconstruct the Rips complex. And the scales are up to 1/3 of the length of the shortest simple loop. If you have no loop and you have a geodesic tree, then everything is trivial. Nothing really happens. So the interesting case is only if your metric graph is not simply connected. How you can prove this thing, it works the same way as the example before. You just construct sets of maximal diameter. Those will be, for these scale parameters, this will be trees, and their intersections will be trees, so everything is a good cover and you're done. You don't need to use any fancy machinery. It works for open Rips complexes, for closed Rips complexes, and you can actually pull it out for check complexes as well. Yeah, and going beyond these scales, how do we see that we do not get a homotopy equivalence? This will actually follow from the next chapter here, just considering the one-dimensional persistence.
And sorry, I just keep having a lot of comments, but and then a comment would be Lori, who's on the call, and her collaborators, they have a version of this for the check complex case, which is quite nice.
Uh-huh. Oh, they have a complete classification of this thing? Oh, no, they have, a result.
Oh, sorry, no, I'm thinking of the one-dimensional persistence. Okay.
Yeah, we'll come to that. I have that paper mentioned later.
Here you're doing homotopy type.
Yeah. Here we're just talking about reconstruction scales. That's what we have here. And later we'll be talking about all scales, but just using one-dimensional thing.
Thanks.
Yeah, thanks for the comment. All right, so that's the second reconstruction result. And the third reconstruction result is this one. Maybe I should mention, maybe just say a story about it. So as I mentioned, the Rips complexes we're talking about here are typically constructed on uncountably many vertices. And the natural question obviously arises, well, what happens if you take only finitely many vertices, take some density, something a person could code and, experiment with. So there is there's a trick using stability result and some other tools that tells you that, well, if you have a nice interleaving of Rips complex and check complex, and you take some sample of your, let's say, manifold, and you just take an image of such a map from Rips complex at some scale to a larger scale, you will actually reconstruct the homology of your manifold. So that's one way of getting some guarantees on how to reconstruct the homology of your manifold. Now, using the approach we're describing in this lecture, we can pull off the same thing with the difference that we don't need to go through various scales. Now, the scales are always R and R here. The only thing we need to do is we need to increase our sample. Now, admittedly, I don't have any bounds on what the densities of this sample have to be, but the conditions are much more relaxed than in the classical case. The only thing I need is well, essentially what I need is just one good cover. Well, the only thing I need is that at scale R, the cover using the sets of diameter R is a good cover. So typically this would hold for small scales. But if you recall the first example that we mentioned today, for small scales, we could reconstruct the space. And then for some scales in between, we weren't able to reconstruct the homotopy type. And then for some intermediate scales, we were able to reconstruct the homotopy type again. So using this theorem, we can hit into those intermediate scales that are kind of isolated from very small scales. So it's a bit more technical. I just wanted to express this thing. Of course, there's a question whether we can do this with a single Rips complex. I have no idea how to do it. It's known that it can be done for manifolds. It was done by Lachev, and also for some nice subsets of a Euclidean space. But in general, suppose you just have a good cover of sets of prescribed diameter of scale R. How do you pick such finite subset? It's not really clear. All right. So much about the reconstruction results. Any question there? Well, I need a sip. All right. So let's go to all scales then. So far what we did is we made a connection between Rips complexes and nerves, and we used that to reconstruct space at small scales. What we want to do now is, well, maybe we just want to focus on one-dimensional homology first, but go through all the scales, and then hopefully get the size of holes or something like that. Now, there are some results along these lines. I think the third one is what you were aiming for before. So Brazos and Fable, they're working on something in wall topology, and one of their technical results is that if you have a nerve of a cover, of a path-connected cover, you can actually completely classify what its fundamental group is. And the same thing actually holds for first homology group. So that's a interesting result that actually comes from another field. Then there are some other papers. Now, in this case, the authors prove some kind of surjectivity in some applications to RIP graphs. And as Henry mentioned in this paper, the authors completely classify one-dimensional check persistence of metric graphs. The way I would like to describe this chapter is just by giving you an example first, maybe build a geometric intuition, and then I'll just give you a result without many technical details. So we'll go by describing an example by Henry and Michal. They actually computed the whole filtration of a circle of circumference ones. So in this chapter, we'll be talking about geodesic spaces, which means that the distance is actually the length of the shortest path segment between 2 points on a space. So we won't be using the Euclidean thing. And in any case, if you the geodesic circle using this metric is essentially the only non-trivial space for which we know the entire Rips and check filtration. Well, intrinsic, not ambient. Okay, so let's see what happens. So if we take, let's say we start talking about Rips complexes of a circle at scales r. We know that for small scales, we'll get something that's homotopy equivalent to a circle. And then at some scale, this thing will break down. And it turns out that the things break down at the first scale when we reach across. By the way, these 3 points are a set of diameter 1/3. If you start constructing, it's a maximal set of diameter 1/3. Whatever other point you add, you're going to increase the diameter. If you take maximal set of diameter less than 1/3, it will always be an interval, but at 1/3, you're going to reach across. And it turns out that at this scale, you actually kill off this one-dimensional homology, which is the only thing we will need for this chapter, but the last chapter, we will also need something else. Turns out that at 1/3, you construct a 3-dimensional homology generator. Actually, you get something that's homotopy equivalent to 3-sphere. And then at some point, something that's homotopy equivalent to 5-sphere, and so on, and until eventually everything becomes contractible. So for this section, we will only want to know about this 1/3 parameter, because this is when one-dimensional homology dies off. But just for later, we will actually be using these higher dimensional things as well. And I really like this result, not just because Henry's listening, but because this, for me, is like, Hopf type theorem. So the classical Hopf result tells you that the pi3 of S2 is non-trivial, which means that the homotopy groups don't really respect dimension really well. And this result tells us that, well, persistent homology doesn't really have much respect for dimensions either, as long as you're taking, well, Rips complexes or intrinsic thing. Working with check complexes, we get essentially the same story. For small r's, we reconstruct the circle, and the first time something goes wrong is at the first scale when you get a configuration of triangles reaching across. The configuration looks like this. So we get it the quarter. And again, we get all dimensional spheres. Okay, so the only thing we need to remember for this section is that once you get a triangle reaching across this geodesic circle, this is at the scale 1/3 of the length of this circle, things die off. Okay, And now suppose you take, let's just say, compact Riemannian manifold, meaning that you have a surface and you measure distances just on the surfaces. It turns out you can completely classify its first one-dimensional persistent homology. Turns out that the Rips and check persistence, one-dimensional persistence, are isomorphic. The only difference is this scale parameter 3/4. This comes from, if you recall the scales when things go wrong, this is 1/3, this is 1/4, and everything else is the same essentially. So these two are essentially the same, which is one of these few examples where you can say that both complexes actually give you the same information. And the persistence actually has the following form. You take your homology, and then as the scale increases, you're just killing off loops by size. So what kind of size are you using? So essentially, this means that those bonding maps will always be surjective. And what kind of size are you using for loops? You can either use length, you can either use the radius of the smallest enclosing ball, or you can use the diameter of the loop. A small comment. Here we have the radius of the smallest enclosing ball kind of equaling the diameter, which is kind of unexpected in the Euclidean case, but notice that what's actually happening is you're killing off homology elements in geodesic circles. And if you imagine a geodesic circle of circumference 1, well, its diameter is 1/2, going from one side to the other is 1/2. And the radius of the smallest enclosing ball will be 1/2 as well, because, well, wherever you put the center, it will have to reach across. All right, and description, which is more in line with persistent homology, is that you essentially just get bars starting at 0 and ending at 1/3 of the length of the appropriate homology generators. So essentially, you're detecting the shortest homology place. So these are formalities. Let's go to an example. Okay, so suppose we take a torus. It's a bit thinner. It's a two-dimensional torus. Yes, it's hollow. Its shortest homology base is A and B. And the persistence diagram will look something like this. If we're doing it with Rips complexes, we'll have depth at 1/3 of the length of the first smallest generator, and then 1/3 of the length of the second smallest generator. And if you want, you can actually reconstruct these generators from critical triangles. You just take vertices of critical triangles and connect them in your space. I had a master's student playing with it, so it's a fun and easy thing. All right, so far, yeah, that's what we have about one-dimensional persistence, at least using infinitely many points. So what I also want to talk about, which is related to this, is what happens if you take a finite sample of this thing. So this is, yeah, one of the few cases where we will jump to finite simplicial complexes. So the setting we have is, okay, so if you have, let's say, again, compact Riemannian manifold, we know what happens with, we know what the one-dimensional persistence is supposed to be. But suppose you now take a finite subspace, we just use the same geodesic distance, and we compute persistence. Now, using stability results, we can imply that we get something really close, but actually in this case, we get a better stability result. So the technical details behind it are the following. So this will be one-dimensional filtration of the whole space. The Rips complexes here will have uncountably many vertices, while here we will have filtration of our sample point. So this is typically what you could compute. And you see that we get as interleaving, which looks very special. So going down, we really go just down. We don't go right at all. Going up, we actually shift to the right by 2s. So we could make it that into proper interleaving where, going up and down goes the same way. But, using this kind of diagonal interleaving actually gives us better result. And we can actually prove that all sorts of maps are surjective. So these maps are surjective, these are surjective. We already know from before that these maps are surjective because, as you said, we start with the first homology and then you're just killing out loops, which means that things are surjective. And these maps on top turn out to be surjective as well, except for the initial stages. And you can actually translate this kind of special interleaving into the following diagram. Yeah. So here's the example from before. This is the ideal case, what we would get if we could compute things with uncountably many vertices. Now, this classical stability using this Gromov-Hausdorff distance gives us this thing. The red point could move anywhere within this gray area. Blue point could move anywhere within this gray area, and we could get all sorts of noise along this diagonal. However, that special interleaving that was mentioned on the previous slide tells us that we're not getting any noise along the diagonal from the scale 2s on. We may get something at the beginning, but from this small scale, which is essentially twice the density, nothing happens. And also these significant points, they cannot move down. They can only move up. And the geometric interpretation is that, well, here you have a loop. And now suppose you want to approximate it by a triangle spanned on 3 vertices going around here. Well, the circumference of that triangle is going to be longer, which means it will take you a bit longer to kill it up. So this is what you get, which means that the thing is fairly stable. We'll see a moral example of this thing at the end of the talk. It actually turns out that the best you can get is actually to keep these death times here as they are. And birth times, of course, they will deviate towards the right. I mean, you cannot have birth time 0 because you're starting with a finite collection of points. So that's something that's going to happen, but still you know that the thing is much more stable than you could think, than you could deduce by only using the standard stability result.
Žiga, the obtainable one, is that not for like an arbitrary S-dense subset, but like there exists an S-dense subset? Okay.
Yes. So this result, this stability here means that, well, if you take S-dense subset, this is what's going to happen. And this one essentially, well, to be a pessimist, there's a probability 0 that you will pick a sample for which this will work. Essentially, you need to have 3 equidistant points on each of these loops to make it work.
Thanks.
All right. Any other question? Anyone? All right. So now we'll go to the last part. Okay, we talked about one-dimensional persistence going throughout all scales. Now we'll try to describe at least some elements of higher dimensional persistent homology going through all scales. And of course, we're interested in surprising things. This is just a recall of result of Henry and Mikal. So just to recall, if you take a geodesic circle with increasing R, you get one-dimensional sphere, three-dimensional sphere, five-dimensional sphere, and so on. So we'll pick this slide, and we'll throw it up here on the left, just for reference. And the example we'll be playing with will be this torus. So this torus has its shortest first homology base consisting of A and B. These are, homotopy / geometric invariant. But there's also this geodesic circle. It's a closed geodesic. C, it's not really significant from homotopy point of view because it's homologous or homotopic to A, but we'll still be able to detect it. So what we will do is we'll start with small r here, and we'll slide it towards the right, and we'll try to include this picture into these geodesics. So for small r, we know that we're working with Rips complexes, by the way, although the same trick could be pulled off for intrinsic check complexes. We know that for small r, we reconstruct the homology of R space. So one component, two one-dimensional elements, and one two-dimensional thing. And then at 1/3 of the length of A, we already know that this bar will cease to exist. But what will actually happen is that the Rips complex generated just by this circle, using this result, will become homotopy equivalent to the 3-sphere. So we could actually imagine a 3-sphere popping up here, and one would expect 3-dimensional bar appearing here. So this is kind of suggesting this hop type effect that, you may have a 3-dimensional bar in persistent homology, but that may be a result of a lower dimensional geometric feature somewhere. All right, that's fun. Let's go on. Now, at 1/3 of the length of C, a 3-dimensional sphere should appear here. Now, this one doesn't kill anything because C doesn't represent any one-dimensional thing, but still a 3-dimensional bar should kind of appear. And if you look, we created a new void in here, kind of a chamber. So before, this was kind of one two-dimensional homology generator, and here we used a wall to, wall it off, literally. So we would expect to get a new two-dimensional homology generator. That's even more interesting. You see, you have a closed geodesic. It's not homotopically significant, but you'll be getting 2- and 3-dimensional homology out of somewhere. So the 3-dimensional homology actually comes from this Henry's result, and this 2-dimensional homology is actually an artifact of the way this geodesic is embedded in here. All right, and then we go on, and again, at 1/3 of the length of B, another 3-dimensional thing arises, and this one-dimensional thing should cease to exist. All right. So that's very nice. It's a few geometric pictures. Can we actually pull it off formally? Excuse me. Yes, we can. I'll just show you two ways of deducing this kind of results. We have to isolate these geometric features that generate higher dimensional homological elements. We can do it either globally via contraction or locally via deformation and contraction. So let me just briefly describe both of them. A contraction means we have one Lipschitz retraction, which means that's retraction onto a subspace, and the distances can only increase or stay at the same level. This one, at every contraction onto a subspace, actually induces retraction on Rips complexes. And then from this, it's actually fairly easy to deduce that the whole persistent homology of this subset, in our case, we're actually talking about loops. Alpha would be a loop, but it actually works for any subset. The problem being that, you know, the circle is the only geometric space for which you know the entire persistence. So that's the one we usually play with. So this whole persistence will actually be included as a direct summand of this whole persistence. So that means that those three-dimensional spheres actually appear there as long as we have a contraction onto those loops. And the other thing is, well, the problem with contraction is that you kind of have to map the whole space. If you want to map something locally or do some kind of condition on a neighborhood, you need to have a different kind of thing. Here is the definition of deformation contraction. Maybe I don't want to go through this thing. What it means is just that it's a deformation retraction, and as you're moving, points cannot go further apart. They have to keep going closer and closer. That's this condition. And it turns out, this was proved by Hausmann, that this kind of deformation contraction, which is a special kind of deformation retraction, induces a homotopy equivalence on Rips complexes. And so, I'm being a bit quick here. If you have a loop alpha, which has a neighborhood, let's just talk about surfaces now. Suppose you have a red loop alpha, and you have this kind of hyperbolic neighborhood. What do I mean by that? I mean, the essential condition is that you can have a deformation contraction of the whole neighborhood onto your loop. Then you can throw this into Vietoris long exact sequence. You need to do some more technicalities. And you can prove that the persistent homology of this subspace of yours is a direct summand of the whole persistent homology. The theorem is stated just for loops, but actually a more general formulation holds for anything. There are only a couple of things I want to mention. This one only works for k being the dimension larger than 1 if we have loops. And it does not work for all scales. It works for scales up to r, where r is 1/2 of the size of this neighborhood. So the distance between this and these two loops is r. So going across from here to here, we have 4r. Meaning that the larger hyperbolic neighborhood you have, the more persistent homology you will detect. Okay, so now if you look at our previous example, well, we can find a contraction of the whole torus onto A. Not hard to imagine, which means that we will get all these one-dimensional, three-dimensional, five-dimensional elements. The same works for B. However, we cannot get the whole contraction onto C. Well, if we had any contraction, then A would have to contract onto C, and then we would have to extend it at some point. However, C has, well, if you look at this size, it has kind of hyperbolic neighborhood. Well, that's what's supposed to be suggested by the image, which means that we can use the previous result to deduce that this three-dimensional bar actually appears. Now, I haven't mentioned this two-dimensional bar. This one needs a different proof, but yeah, that's a different thing. Okay, any question at this point? I only have one more slide. It's just an example. All right, example. So this is something that my master student was playing with. We take a sphere of radius 1, and we cut out the top cap, and we get this red geodesic. Now, if we had the whole sphere, this wouldn't be a geodesic on the whole sphere, but once you cut up the top, you know, this is like the shortest path between this point and this point. This one is of well, the radius of this circle that we cut out here is 1/4. And then, well, we threw in finite sample. I forgot what size. We generated geodesic distance, and we threw everything into Ripser, and this is what we got. And the surprising thing is that one can actually, we're talking about things being stable here, one can actually interpret everything that's here. So for example, these are one-dimensional homology elements. These are actually artifacts of the, we started with a finite collection of points. So, those points will be connecting, you'll be getting some small loops. We could improve these longer bars just by taking a better sample. Now, there's nothing significant one-dimensional happening here because, well, there's nothing significant one-dimensional happening here, but we do have an appearance of a two-dimensional bar along with this pixel here is supposed to be green, in case you don't see it. We have a very short three-dimensional bar. And they both appear at 1/3 of the length of this circle. So you could interpret this fact that, well, if you have two and three-dimensional bar appearing at this scale, you probably have a geodesic circle of 3 times this scale lying somewhere there. Why is this one so short? Well, this is approximately as short as it's supposed to be by Henry's result, so not surprising. These are just the scales that pop up in that theorem. This thing is kind of longer. It dies out at 1/3 of the length of the equator, so this one kind of detects that thing. And these short things, they actually appear as three-dimensional spheres, just as this one, corresponding to the equatorial circles. These are all geodesics going around here. They do not have a hyperbolic neighborhood as we were talking before, but they still, well, there's a bit more evolved reason, you can still detect them around here. So the point is that interpreting this persistence diagram, there's nothing that one cannot explain, right? We took some sample that's of some Grommelhausdorff distance close to it, except for these short bars which start, there's no way to get around them. There are no random short bars popping up here or there or anywhere. You can actually detect all of it. And these 2- and 3-dimensional bar actually point out to one-dimensional geometric feature. So this geodesic circle, it's contractible. So from the point of view of homotopy, it's insignificant, but you can still detect it. There's a short 2-dimensional bar here, but that's also an artifact, so it can be. Yeah, by the way, this example also disproves Hausman conjecture. I think my time is up, unless I'm mistaken. Henry?
Oh, I didn't know if Sarah's...
Yeah, I'm also here.
Okay. Yeah, you should just finish up Žiga, and I don't know if you had the future directions, but finish up, and then Sarah will solicit questions.
Yeah. So maybe I just have. Well, this is the last. This is really the last slide. This is the one slide I could usually skip. We're working on this flow that I actually presented here. First, we want to determine filtrations for persistent homology of simple spaces like Henry did for circles. Then we want to detect nice embeddings. So there work on being done on how large a hyperbolic neighborhood you can get and what kind of contraction you can get. And then the third part is to determine effect on persistent homology. So far, at least in the case of circles, we saw how to prove the existence of those odd-dimensional spheres, but proving the existence of these 2-dimensional bars is kind of more technical. And presumably, in higher dimensions, things get more complicated. So we can extract various geometric features, components, short as homology base with lengths. So that has some geometric information. Lengths of all sorts of geodesics, even if they're contractible, and locally minimal spaces, which means that, if you have a geodesic subspace, or you don't even have to have a geodesic subspace, if you have something where a subspace has this hyperbolic neighborhood, you're going to detect a part of its persistent homology in the larger, in the persistent homology of the whole space. So that's kind of a clue of what kind of things we're aiming for. Okay, now I'm out of slides, so you guys have to take over.
Very good. So any questions that were not asked during the talk? Yeah, so if you have questions, do unmute yourself.
I have a question, Žiga.
Yeah.
So you were talking about this torus that was sort of bumpy, and you had this not only alpha and beta, but also C. Yeah. But pretend you had like the flat geodesic torus, right? So your results prove you get these features coming from A and coming from B. Like, would you conjecture that's all of the persistent homology, or like, do you think that's a reasonable conjecture of the entire persistent homology of that torus, or do you think there's more, or any guesses there?
You mean with this kind of example?
Flat torus with like the L2 or geodesic metric.
So just S1 times S1. Well, in that case, you will not get a two-dimensional bar.
That's right, but that's coming from C. Like, but
Yes.
you prove that you'll get all these things coming from A, and you'll get all these things coming from B. I guess you'll also get the two-dimensional homology of the torus.
Yeah. So actually, I think that initially that was my conjecture, but then we were discussing some options with some people, including you, and I did some experiments with Ripser, and all sorts of other things started popping up. So morally, I still don't see what else can happen, but it's just not clear. So that would still be my conjecture, but I would be much less confident about it. I mean, that would still be my conjecture, just for the reason that I have no better conjecture.
Yeah, clearly neither do I.
Yeah.
Another question. So you had this retraction result that was for a loop alpha with homology dimension above 1, but you said you can do it for more general things besides loops.
Yes.
What happens to that homology restriction? Does that homology restriction change? Like if alpha is not a loop, if it's something more general, do you have to rule out more homology groups, or?
Yeah, this thing actually depends on what persistent homology of your subspace is. So if you're a loop, you're not going to detect the loop, which is why you're not going to detect one-dimensional persistent homology. But then, the Hausmann's conjecture holds for this thing, right? So for larger scales, these persistent homology generators are actually increasing in dimension. So in that case, you will get something similar. But if you have, I don't know, some strange torus where, some new one-dimensional things start popping up, I don't know, maybe you would have to put some different restriction. But maybe a comment I want to put here is, with this nice neighborhoods thing and with this contraction result, you don't really need geodesic spaces here. This works for anything. So Henry, I think you have some results on persistent homology of ellipses and regular n-gons. if that one is a subset of your manifold, even if you're doing with Euclidean metric and doing Rips complexes there, you can still detect things. So these theorems are fairly general. But yeah, to go back to the question, yeah, this thing may change and it's not really clear how. It will depend on the subspace.
Thanks.
Okay, so in that case, I would suggest that we finish. So, if there are any other questions, let's do them offline, just because, we've been here for about an hour. So I want to thank Žiga again for giving the talk. And I would also like to remind everyone that the next talk will be on October 9th, on Wednesday, but not at the regular time. So we're going to meet at noon, and it will be, and the speaker will be Catherine Hess. So that's it. Thank you. I will stop the recording now.